Very good morning, students. Welcome to our learning channel platform. As you all aware of the previous videos regarding fundamentals, we are covering fundamentals of matrices under topic 1. So in topic 2, we are going to cover operations on matrices. Operations on matrices. So here operations, generally there are 2, but we will take it 4. There are operations: addition, number 2, multiplication. So you may be wondering, what about the remaining 2 operations, subtraction and division? Speaking, in your numerical techniques or whatever you say, number system, only 2 basic operations are defined. One is addition, other is multiplication. If you add the result, we name it as sum, S-U-M. If you multiply the result, we name it as a product, P-R-O-D-U-C-T. So why other 2 operations we are going to discuss? Note. Third one, what you guess? It is subtraction. And fourth one, division. Subtraction is also called as here difference. Division is also called as quotients. Subtraction or difference, it is a part of addition. Part of addition. The same way, division or quotients, it is part of multiplication. That's why we give importance for these 2. If you know addition, automatically you are going to get difference. If you know the concept of multiplication, you can understand the concept of quotients. That's why we are not going to discuss separately the 4 operations, only 2: addition, multiplication. Here note points I gave you: subtraction or difference, it's a part of addition; division or quotient is a part of multiplication. So how these 2 operations are defined on matrices? What are the conditions to add to matrices? What are the conditions to multiply to matrices? These 2 play a vital role. And with the help of this addition and multiplication, algebra of matrices can be defined. Algebra is nothing but without using numbers. If you are going to use only alphabets, lowercase letters or uppercase letters to deal the properties mathematically, that contest is called algebra. Algebra of matrices means we are going to use only notations of the matrices or name of the matrices to define some properties. Slowly, what are those properties? In coming videos under part 1, part 2, part 3, we are going to cover. So for time being, this is the first one. We can highlight part 1. How many parts we are going to get, it depends upon the contest. So it's a part 1. We are discussing about these 2 operations and operations on matrices. Okay, let us continue. First operation is that addition of matrices. So here minimum 2 matrices are required. First one, what are the things you have to be ready with to perform addition? First, 2 or more. 2 or more matrices are required. Number 2, the size. The size means how many rows, how many columns. The size must be same. So to perform addition operation, what are the requirements? Minimum 2 or more matrices can be considered are required. To add matrices, what is the condition? This is the most important one. It's also called condition. Condition to perform addition of matrices or sum of the matrices, the size must be same. The size must be same. If sizes are different, addition is not permitted. You can't add the matrices. How to add matrices? When you know these two, we have two or more matrices and sizes are same, or size of each matrix is same. If these two are ready with you, then you can add matrices. How to add them? So the thing is that we add the corresponding elements. That's all. Corresponding elements. The rule. It is called the rule. Corresponding element means if you take two matrices, the element of first row, first column will be added to the element of first row, first column of second one. First row, second column adding with first row, second column of other. I'll quote one example so that it is very clear to you about the rule. We add the corresponding elements. How to add matrices is only one rule, is a condition. Minimum two or more matrices are required. Let us see the example. Here, a small example to understand. We have taken two matrices with a different naming. One is capital A, one is capital B. You see here, as per the requirements, the first one is fulfilled. Two matrices must be there to compute addition. Two matrices. You see a size 2 by 3, 2 by 3. I told you the condition is that if you add two matrices, the conditions are satisfied here. Order or size is same. And how to add matrices, I told you the corresponding elements are added. So we show A plus B like this. A plus B. It is called sum. Sum of A and B. A plus B stands for sum of A and B. SUM sum. So as usual, we copy the first matrix 1, 4, 2, 2, 9, negative 2. 2 by 3 plus second matrix 1, 7, 2, 0, 6, 5. Same size 2 by 3. I told you the corresponding elements. So these are the corresponding elements. I'll highlight so that you can able to understand. First row, first element, these two are corresponding. 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 So I highlighted with arrows. 1 and this one, they are corresponding elements. 4 and 7, they are corresponding elements. 2, 2, 2, 0, 9, 6, negative 2, 5. These are the corresponding elements, what I mentioned there. The result or the sum I am writing here, just 1 plus 1, it is 2. 4 plus 7, it is 11. 2 plus 2, it is 4. 2 plus 0, it is 2. 9 plus 6, it is 15. Negative 2 plus 5, it is positive 3. Here, the sum of the two matrices will have the same size, 2 by 3. 2 by 3. If the sizes are different, this is not defined. You can't find the sum. That point, you keep it clear. Two matrices are required and size of the matrices, how many you pick or how many you select must be same. And how to get the sum of the matrices, whether you add 2 or 3 or 4, the same thing. We have to add the corresponding elements of every matrix under consideration. So they occupy like this. The size of the result or the sum will be same. Next example I would like to give. We can take a row, two rows we can add. if it contains same number of elements. Two columns we can add if they contain same number of elements. Because row-wise addition, column-wise addition also possible. Here matrix, 2 rows, 3 columns. Next we cover the second operation, multiplication of matrices. Let us discuss about the second operation, multiplication of matrices. Here also I would like to give the same style, minimum 2, right? 2 or more matrices are required, just like sum. Second one, condition. Condition. So in your first operation and addition, which matrix you are going to take, which order you are going to take, it is not a matter. Whether you find A plus B or B plus A, their order preference is not required. Whether you want to take A first or B next. But in the case of multiplication, be careful, because multiplying A, B, multiplying B, A, they are totally different. They won't give you same product. So that's why this condition is most important to multiply matrices. Here, first matrix, number of columns of first matrix, whatever you take, A or B, must be equal to number of rows of second matrix. It's a condition. So you need to remember the condition, number of columns of first matrix 1m must be equal to number of rows of 2m. 1m indicates first matrix, 2m indicates second matrix. C stands for number of columns, number of rows. Or you can just remember number of columns of first matrix equal to number of rows of second matrix. If this condition fails, you can't able to multiply the matrices or find the product. Note, the order matters in multiplication. Means which matrix is taking the first place. It may be A, then if it is A, its columns, number of columns must be equal to number of columns of B. If you take B here, number of columns of B must be equal to number of rows of A. So which matrix is on left hand side, be careful. This is the most important thing. Order matters in multiplication of matrices. Matrices. And this is a condition. How to multiply? That is the next criteria. Just like in addition, we add corresponding elements. Here also, the same manner. How to multiply? How to multiply? How to multiply? We take, there I took, we add. We take, I write here SOP. SOP stands for sum of the products. Sum of the products. SOP. Sum of the products of the corresponding elements. You know, same thing, but this is the thing you have to follow. Sum means addition, product means multiplication. If you multiply two numbers, for example, 5 into 4, 5 into 4 gives 20. 20 is called product. The result of multiplication is called product. So, product A11 into B11. What is A11? Element of first row, first column. What is B11? Element of first row, first column. To multiply them, we get a product there. Plus, next, A12 into B12 plus A13 into B13. That is the meaning of sum of the products of the corresponding elements. For example, I'll take a row matrix or row contains few elements. I'm taking 4, 9, 3. And I'll take column matrix. The column also must contain 3 elements. First criteria, -1, 4, 4. So, as an example, I took a row matrix and a column matrix. Easy to understand. For multiplying two matrices, you take any row as you wish. You can take 3 elements or 4 elements, because only one row, if keep on increasing elements in that, columns are going to increase, but row will be only one. Similarly, you take a column matrix. As I said in the beginning, when you write the size, row number first, column number next. So when you want to multiply these two matrices, first row matrix, then column matrix. R into C, RC, RC rule. RC rule. If you understand this idea, the same thing we extend. We take a row and a column, row and a column, row and a column. That we extend for different size of matrices based on that condition what I told you. Number of columns of first matrix equal to number of rows of second matrix. Simple to understand. You take one R, one C. RC rule we have to apply. That we will see shortly. So let us understand what is RC rule. So I took a different row matrix, a different column matrix. You see, R, a row matrix, 1 row, 4 columns. A column matrix, 4 rows, 1 column. 1 column, column matrix, 1 row, row matrix. RC rule. So here the matrix product, first one, if I want to compute R dot C, RC rule. First always rows. So how you write? R, whatever the matrix you take on right hand side, you take the transpose of it. Already you know what is transpose. In the previous part of the video I covered. Transpose means if you have a row, it becomes column. If you have a column, it becomes row. It becomes a row. So extending row, first one, -1, 2, 9, 3. No need to show the size here. Dot. Here what I took? C power T. C transpose. It is C transpose or transpose of T. Transpose of C. Initially it is standing like a column. Now it becomes row. Transpose, no? Row. What is become? 1, 0, 4, 5. It looks neat now. This becomes row here. Now these are this one and this one. I'll highlight. Be careful with this. Corresponding elements. Corresponding elements. Corresponding elements. Corresponding elements. I write here corresponding elements. Identification of corresponding elements. I just showed you. What I gave the result? SOP. SOP. Sum of the products. Means sum of the products of corresponding elements. -1 into 1. is a product. Multiplying corresponding elements minus 1 and 1, which become product there. It is product P. Plus, it is sum. Sum. Next, 2 and 0 is a product. Plus, sum. Next, 9, 4. Multiplied, these two multiplied. It is product. Plus, it is sum. Last, 4, or it is 3. 3 and 5. Just check it out. Minus 1 into 1, product. Plus 2 into 0, product. Plus 9 into 4, plus 3 into 5. No need to write all these things. Just for idea's sake I gave you. Because of SOP I wrote. Just you can directly identify like this. No need to show also. Understood. Each row and each column must contain same number of elements. That you keep in mind. Because anyhow we get same fashion. 2 rows we get. 2 rows we get. We multiply corresponding elements. You take the sum of it. So what is the result here? Negative 1 plus 0 plus 36 plus 15. Result minus 1 plus 36. It is 35 plus 15. It is 50. So when you take a product of a row and a column transpose, we get a pure number. Sometimes it is also called a dot product of two vectors. Dot product of two vectors. This idea we are going to extend for each row and each column, depends on size of the matrix. That we will cover in next example and conclude the video. Let us apply that RC rule. If you apply RC rule, the result will be a pure number. That pure number will occupy one position in the matrix. Means the corresponding element position in a matrix finally. RC rule method. You see, now I want to find out, here I have taken A is a square matrix 3 by 3. Here size is 3 rows, 3 columns. B is a rectangular matrix, size is 3 by 2. You see, columns of first matrix are equal to rows of segment. Condition satisfied. Condition satisfied. Left over is 3, left over is 2. The product matrix will contain this order 3 by 2, 3 by 2, 3 by 2. So A into B. Here order matters. Possible. A into B possible. I write generally C. Always you take a matrix C. C is the product. C is the product. Product of A and B. So how C contains what elements? Because here leftover is 3, it contains 3 rows. By leftover is 2, it contains 2 columns. So you know how to name that matrix C. Already in the beginning I gave you. It is C11. It is C12, C21, C22, C31, C32. Let us write clearly. It is C12, C22, C23. Now we have to find out what is this value. Corresponding element of C is this one. C11, C12, C21, C22, C31, C23. These elements we are going to find out now by applying that RC method. RC method. RC method. To get C11, what you will do? Instead of doing inside the matrix, better you do it separately. First C11. How you get? We get R1 into C1 transpose. B1, B. Just wait. I took AB there. To avoid confusion, first matrix A, I write 1. 1 stands for row number. First row, like this. Next B is there. I take B1 over T. There I took R into C power T. Row into column transpose. That idea I am going to explain now. Right? Here 1 indicates what? I write clearly, select row 1 of A. This one, select column 1 of B and take transpose. Now it's clear to you. This logic we have to apply to each. C12 means row 1, column 2. C21, row 2, column 1. Let us extend in next video continuously how to perform this. Just a small correction. It is third row, second column. Please make a note of it. Just corrected. It is third row, element of third row, second column. I wrote reverse by oversight. Sorry. Now how to perform this? I am going to wipe off this one and write separately. Just you have to be stick on to this simple rule to get the result. So what you get here? C11, I wrote A, select row 1 into, in B, select column 1, take its transpose. So what is row 1? 1, 2, 1. What is column 1? 1, 4, 3, because we took transpose. Now, sum of the products, we get 1 into 1 plus 2 into 4 plus 1 into 3. That is equal to 1 plus 8 plus 3. 9 plus 3 equal to 12. Therefore, our first row, first column element in C product is 12. 12. Next, C12. How to write C? How to get C12 value? It is in row in capital A or the first matrix, select row 1 into, in B matrix, take second column, its transpose. Row 1, 1 to 1 over into transpose of column 2, 216. Sum of the products, 1 into 2 plus 2 into 1 plus 1 into 6. That is 2 plus 2 plus 6, it is 10. Therefore, C12 element value is 10. Hope you followed. Now, C21, second row, first column. Here, from matrix A, you take second row into, from matrix B, you take first column, take transpose. So, what you get here? Row 2, we have to select there. 0, -1, 1 into column 1, transpose 1, 4, 3. Apply SOP method. 0 into 1 plus -1 into 4 plus 1 into 3. Sum of the products of corresponding elements. We get 0, -4 plus 3. We get -1. C22. C22. So take column 2 of A, column 2 of B, take transpose. So column 2 of A is 0, -1, 1 into column 2, 2, 1, 6. Apply SOP, 0 into 2 plus -1 into 1 plus 1 into 6. Compute 0, -1 plus 6, that gives plus 5. Therefore, C22 is equal to 5. Hope it is clear to you. Two more elements are required now. Clear? So if you compute like this, it looks neat, and without error, you can able to get the product. Next, third row, first column, C31. Select row 3 in matrix A into select column 1 in matrix B, take its transpose. So what is row 3 here? 1, 1, 4. What is column 1? 1, 4, 3. Apply SOP, sum of the products of the corresponding elements, 1 into 1 plus 1 into 4 plus 4 into 3. Compute 1 plus 4 plus 12. This comes to 5 plus 12. It is equal to 17. C31. And last element of the product, capital C, that is C, third row, second column. From matrix A, take third row into from matrix B, take second column, take transpose. Column 3, 1, 1, 4 in matrix A into column 2 transpose, 2, 1, 6. Apply SOP, 1 into 2 plus 1 into 1 plus 4 into 6. Compute, it is 2 plus 1 plus 24. That is 3 plus 24, that is equal to 27. Last element of C. Therefore, C is given by the elements what you inferred. First is 12, second is 10, negative 1, 5, 17, 27. That is the product of AB, which is equal to A into B. So you can do it inside. It is very messy if you work out all these things here, 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 here like that. You have to move. You have to make use of large space. To avoid that space, each element you compute carefully and dump there. That is your AB. Is B is possible? B into A. B into A. If I want to compute, what is the order of B? Order of B is, I will separate here. Order of B is 3 by 2. What is order of A? 3 by 3. You see, the columns of B not equal to rows of A, not possible. Not defined, you can write. You cannot compute. We cannot find B into A. A into B is possible. First check the condition and do like this. I hope this video is clear to you. Please like, share and subscribe to our channel, to your friends and also all students community who are interested with. So keep learning. God bless you all.